Good morning to all of you. In previous sessions, we had discussed about various properties of Z transform. Right. Today, we'll be discussing rational Z transform. So here in rational Z transform, we'll be looking at what is zeros, what is poles, right? So initially, we will define zeros. Okay. Before this, we have already discussed about region of convergence, right? That is ROC. So ROC is nothing but all values of Z for which x of Z is finite, right? We've seen this. Okay. So here we'll be defining zeros. So the zeros of the Z transform x of Z are the values of Z for which x of Z is equals to 0. Okay. So the zeros of the Z transform x of Z are the values of Z for which x of Z is equals to 0. Okay, so that means we will be identifying values of Z for which x of Z is equals to 0. Right? So such values of Z will be called as what? Zeros. Right? Before this, we have seen the definition of ROC as well as we have plotted the ROC on real and imaginary plane. Okay, by drawing particular circle and indicating the interior, exterior, or some other part of that plot as ROC values. Right. Similarly, there is definition for poles. Right. So basically, the poles of the Z transform x of Z are the values of Z for which x of Z is equals to infinity. Okay. So the poles of the Z transform x of Z are the values of Z for which x of Z is equals to infinity. Okay, so if x of Z is infinite for any value of Z, then it will be included in the set of poles. Okay, so while defining this rational Z transform, if this x of Z, that is Z transform of x of n, okay, this x of Z is nothing but, if we have discrete time signal x of n, and if we are identifying the Z transform of it, then it will be indicated as x of Z, and this x of Z as per the formula is nothing but what? Summation n is equals to minus infinity to infinity x of n into z to the power minus n, right? This x of Z is equals to summation n is equals to minus infinity to infinity x of n into z to the power minus n. These things we have already discussed, right? So if x of Z, okay, is the rational function, so what does it mean? If it is a rational function, then this x of Z can be represented as comprising some numerator values and values in denominator. Okay, so if x of Z is represented as some rational function having some standardized form as b0 plus b1z inverse, right, plus b2 z to the power minus 2 plus and so on plus b and z to the power minus m. Okay, so b and z to the power minus m. Okay, so these are the values present in the numerator, and in denominator it has a0 plus a1z inverse plus a2 z to the power minus 2 plus and so on plus a n z to the power minus n. Okay. So this function can be represented in more compact way as summation. Here I can say that k is equals to 0 to m. Okay, so as you can see here the coefficient or the b0 is multiplied with z to the power 0, right? So z to the power 0 is 1, so simply b0 has been written here, right? So I can represent it as summation k is equals to 0 to m bm z to the power minus, sorry, not bm, bk. Okay, bk z to the power minus k, right? So if I'm substituting the values of k here, so it will be b0 z to the power 0 plus b1 z inverse plus b2 z to the power minus 2 and so on plus bm z to the power minus m. Similarly, in denominator we can write summation k is equals to 0 to n ak z to the power minus k. Okay, so what we have done here, we have represented this x of z as in numerator and denominator form in rational, as a rational function, right? So if this b0 and a0 are not equals to 0, so in that case we can avoid these negative powers of z by factoring out the terms b0 z to the power m and uh, a0 z to the power n. Okay, so if we are considering this a0 and b0 are not equals to 0, right? So how this can be represented, this function, just for example I'll be modifying this x of z. Okay, so this x of z can be represented as, again, it comprises numerator and denominator. Okay, so from numerator, if I am taking b0 z to the power m common, okay, from each term, that is b0 z to the power m from numerator, and from denominator I will be taking a0 z to the power minus n, a0 z to the power minus n. Okay, so here what we are considered, what if b0 is not equals to 0 and a0 is not equals to 0, so it has certain value present here. So if we consider b0 is not equals to 0 and a0 is not equals to 0, and we take b0 z to the power minus m and a0 z to the power minus n common from the numerator and denominator, right? So what will remain in numerator? So it comprises, in first term we have taken b0 and z to the power minus m common, so it should have z to the power m there in first term. Okay, so if you multiply b0 z to the power minus m with z to the power z to the power m, so this z to the power minus m plus m will be z to the power 0, so z to the power 0 will be 1 and only b0 will be there, right? Similarly, then next one will be, it will be b1 divided by b0, right, into z to the power n minus 1. Okay, so what we are trying to do, we are trying to eliminate the negative powers of z, okay, from the numerator as well as from denominator. Okay, so plus and so on, plus the last term will be simply bm upon b0, right? That will be last term, right? Similarly, in denominator we'll get z to the power n, okay, plus this a1 upon a0 z to the power n minus 1, right, plus and so on, plus an upon a0, right, correct? So this n of z and d of z are polynomial in z, and this can be expressed in factorized form as, because this is mth order and nth order polynomial, right? This is mth order and this is nth order polynomial. So this numerator will have capital M roots, right? Similarly, this denominator will have capital N roots, right? So here we can represent this x of z again as in numerator and denominator as a rational function as so we can take this b0 and a0 will be the constant. If I'm sending z to the power minus n in numerator, so it will be z to the power minus m plus n will be there, right? Multiplied by, as this numerator will be having m roots, capital M roots, and denominator will be having capital N roots. So if I'm considering those m roots at z1, z2 up to zm, so this can be represented z minus z1 into z minus z2, right? And so on up to z minus zm. Okay, so it has capital M roots because it is a mth order polynomial. So it is nth order polynomial, so I can represent it as capital N roots as p1, p2 up to pn. So I can represent it as z minus p1, z minus p2, and so on z minus pn. Okay, so from this x of z we can say that if I am substituting z is equals to z1, okay, so this will be 0, as this will be 0, so everything will be 0, okay, because z1 minus z1 will be 0. If I am substituting z is equals to z2, right, so it will be z2 minus z2, so it will be 0, okay, so everything will be 0. So as we have seen in the previous slide, the definition of zeros as zeros of the z transform x of z are the values of z for which x of z is equals to 0. So that means this x of z here in this case, this x of z has capital M zeros, okay, that is z1, z2 up to zn. Similarly it will have capital N poles, because if I am substituting z is equals to p1, so p1 minus p1 will be 0, 1 upon 0 will be infinity, so everything will be infinity, right? So similarly, if I'm substituting z is equals to p2, so p2 minus p2 will be 0 and it will be 1 upon 0, so it will be infinity. So it will have capital N poles as p1, p2 up to pn, right? So I'll just rewrite this last function here once again. So that what is that? X of z representing a numerator and denominator as a rational function, and it comprises p0 upon a0, right? Multiplied by what is that? Z to the power minus m plus n is there, right? And it is multiplied by z minus z1 multiplied by z minus z2, okay, and so on z minus zm, okay. Similarly z minus p1 multiplied by z minus p2, right, and so on z minus pn is there, right? So again, in more compact way, you can represent this x of z as, if I'm considering this b0 a0 as any constant, just for example I'm representing it with capital G, z to the power I can write n minus m, right? And here these terms can be represented because it is the product of these terms, that is z minus z1 multiplied by z minus z2. So I can take it as product of, okay, product, where I can take the variable k starting with 1 ending at capital M, okay. So k is equals to 1 to m z minus zk, right? Z minus z in suffix k. So it is product of z minus z1, z minus z2, z minus z3 up to z minus zm. Similarly, in denominator I can write k is equals to 1 to n z minus pk, right? So it will be z minus p1, z minus p2, and so on, right? So in above equation, that is x of z, okay, where this capital G is equals to simply b0 upon a0 were taken, okay, b0 upon a0, okay. So we can say that this x of z, okay, has x of z has how many zeros? As per this numerator there are capital M zeros, okay, has capital M zeros at values z is equals to z1, comma z2 comma and so on up to zm, because if we are z in suffix capital M, because if we are substituting any one of these values of z in this equation, so this will be 0. So it has m zeros at z is equals to z1 z2 up to zm. Similarly, it has capital N poles, again these values of zeros and poles are finite because it has certain values z is equals to z1 z2 up to zn. So it has capital N poles at capital Z is equals to what? P1, P2 and so on up to Pn. Okay, so if you are substituting any one of these values in this equation, so it will be infinity. So it has capital N poles. Okay, we have seen the definition of zeros and poles here. Zeros are the values of z for which x of z is 0. Poles are values of z for which x of z is infinity. So if you are substituting any one of these values of z in the above equation, that is p1 p2 up to pn, then it will be infinity, therefore it has n poles. Okay, and depending on the values of capital N and capital N can be less than m, or if it can be greater than m. Okay, so it has what you can say that mod n minus m zeros, right? It has n minus m zeros if what, n is greater than m. So if n is greater than m, so this will be positive. Okay, so if it will be positive, then you can say that it has n minus m zeros, right? But again here mod, right? And the same poles will be there, right? If what, n is less than m. Correct. So again it will be at origin, that is at z is equals to 0. Okay, so this there will be pole at z is equals to 0, depending on whether this relationship exists or not. Okay, even the zeros can occur at z is equals to infinity if you are substituting the values of z is equals to infinity if n is less than m, right? So if n is less than m, so at z is equals to infinity, the zeros will occur, right? So a zero exists at z is equals to infinity if x of infinity is 0, and pole exists at 0 if x of 0 is, so here we can say that uh, 0 exists at z is equals to infinity if x of infinity is 0, and a pole exists at z is equals to infinity if x of infinity is equals to infinity, right? So x of z has exactly same number of poles as zeros at 0 and infinity, right? So this x of z can be represented by using pole 0 plot. Okay, before this was in the ROC plot, right? So in ROC plot we have plotted the ROC, and ROC is nothing but the values of z for which x of z is finite. Okay, here we can also represent this x of z by using pole 0 plot. Okay, so on this pole 0 plot, the location of poles are represented by crosses. Okay, it will be represented by this cross sign. Okay, while the location of zeros are represented by circles. Okay, so we can use these crosses to represent poles on pole zero plot, and we can use circles to represent zeros on pole zero plot. Okay, so here we are seeing the definition of poles as well as we are seeing the definition of zeros, right? So we'll be representing x of z by using pole zero plot. On this pole zero plot, we'll be using crosses to indicate the location of poles, and we'll be using circles to represent the location of zeros, right? So in this session, we'll discuss about rational Z transform. We have seen the definition of zeros, we have seen definition of poles, we have seen one representation of x of z as a rational function where we have represented this rational function in a more compact way. We have factorized these numerator and denominator to identify capital M roots. So we identified capital M zeros, okay, from these capital M roots of numerator, and capital N roots are there for denominator. So there are capital N values of poles, and depending on the values of N and M, where it is greater or less than the relationship, that is N is greater than M or N is less than M, so there will be zeros and poles accordingly. Okay, so here there are m zeros because there are m roots of the numerator, and n poles because there are n roots of denominator. Okay, and a zero exists at z is equals to infinity if x of infinity is 0, and a pole exists at z is equals to infinity if x of infinity is infinity, right? And this x of z can be represented by using pole zero plot. The location of poles will be represented by crosses, and location of zeros will be indicated by circles on the pole zero plot. So in next session we'll be obtaining a pole zero plot from x of z by identifying the z transform of the given discrete time signal x of n. We will initially identify the z transform x of z, and from that x of z we'll try to identify the pole zero plot, and we'll be indicating the location of poles and zero on that pole zero plot. So that example we'll discuss in the next session. Thank you for joining this session.